The James Webb Space Telescope stands as the pinnacle of human ingenuity and the premier observatory in the field of space science. Its mission stretches across the cosmos, seeking to uncover the deepest mysteries of our solar system, investigate distant worlds orbiting far-off stars, and probe the very structure of the universe itself. But beyond simply gathering data, JWST is helping humanity answer some of the most fundamental questions we have ever asked. Are we alone in the universe? How did life begin? And what forces have shaped the cosmos over billions of years? Recently, astronomers pointed JWST toward a star located approximately 120 light-years from Earth. The target of this investigation was a remarkable exoplanet known as K218b, a world that has captured the imagination of scientists and enthusiasts alike. What the telescope revealed in its initial observations has sent waves of excitement through the astronomical community. The presence of carbon-based molecules in the planet's atmosphere, chemical signatures that could hint at the possibility of life. K218b is no ordinary planet. Classified as a sub-Neptune, it occupies a size category that falls between Earth and Neptune, a group of worlds that are strikingly common across the galaxy but completely absent in our own solar system. With a mass estimated at 8.6 times that of Earth and a radius 2.6 times larger, K218b is cloaked in a thick, hydrogen-rich atmosphere, beneath which scientists suspect lies a vast global ocean. Unlike rocky planets such as Earth or Mars, or gas giants like Jupiter and Saturn, sub-Neptunes like K218b defy easy categorization. Their sheer size, composition, and distance from their host stars make them enigmatic worlds, challenging our models of planetary formation and habitability. One of the most fascinating aspects of K218b is its orbit around its host star, a cool red dwarf named K218. The planet resides in the so-called habitable zone, the region around a star where temperatures could allow liquid water to exist on its surface. K218b orbits at just 0.18 astronomical units, far closer to its star than Earth is to the Sun, completing a full orbit in just 13 Earth days. While such proximity would typically spell disaster for a planet orbiting a Sun-like star, red dwarfs emit far less energy. As a result, K218b is not scorched, and its potential for liquid water remains intact. JUIC's instruments have provided unprecedented clarity, capturing the light from K218b's host star as it passes through the planet's atmosphere during transits. This method, known as transmission spectroscopy, allows scientists to identify the molecular composition of a planet's atmosphere by analyzing the unique fingerprints left in the starlight. Early observations detected methane and carbon dioxide, both critical components of life as we know it. But the discovery that truly captured the imagination of astrobiologists was the potential presence of dimethyl sulfide, or DMS. On Earth, DMS is almost exclusively produced by microscopic marine life, particularly plankton in the oceans. Its presence in the atmosphere is a reliable biomarker for biological activity. Detecting such a molecule on a distant exoplanet would be groundbreaking, suggesting that life, or at least prebiotic chemical processes similar to those on Earth, could exist far beyond our solar system. While further confirmation is needed, the tentative evidence of DMS in K218b's atmosphere represents a tantalizing hint that we may have found a world where life could exist, or at least where the conditions for life are present. Of course, habitability is not guaranteed. K218b's enormous size means it likely has a high-pressure mantle beneath its thick atmosphere, possibly composed of exotic forms of ice or supercritical water. The dynamics of its oceans, if they exist, remain unknown, and it is possible that the water is too deep, too pressurized, or chemically distinct to support life as we understand it. Yet, even in the absence of confirmed life, the planet represents a critical step forward in our search for habitable worlds. The detailed spectra captured by JWST provide the most comprehensive view yet of a sub-Neptune in the habitable zone, allowing scientists to model the planet's climate, atmospheric composition, and potential for hosting life with unprecedented precision. Beyond K218b, JWST has been reshaping our understanding of the universe itself. In distant galaxies, the telescope has detected complex organic molecules known as aromatic hydrocarbons. These carbon-based molecules, which on Earth are associated with petroleum, coal, and smog, were observed in galaxies formed when the universe was less than 10% of its current age. Their presence challenges conventional cosmology, showing that the building blocks of life could form far earlier in the universe's history than previously thought. For example, the galaxy SPTO 41847, observed by JWST, appears to have generated massive amounts of carbon and oxygen despite being only a fraction of the Milky Way's age. This rapid chemical enrichment suggests that star formation and the creation of complex molecules were underway within the first 1.5 billion years after the Big Bang. It is remarkable to consider that the universe, still in its infancy, was already capable of producing such chemically rich environments. JWST's ability to detect these molecules at such incredible distances allows scientists not only to map chemical evolution in the early universe but also to explore the environments where life-essential elements first appeared. By comparing the chemical composition of ancient galaxies to that of modern galaxies, researchers can trace the cosmic pathways that led to the formation of stars, planets, and potentially habitable worlds like K218b. This telescope, sometimes described as a time machine, provides humanity with a direct window into the early universe, allowing us to witness cosmic events that occurred billions of years ago. Its observations continue to challenge our assumptions, push the boundaries of our knowledge, and inspire new questions about our place in the cosmos. Each discovery, from the chemical fingerprints on K218b to the complex organics in ancient galaxies, brings us one step closer to understanding the profound processes that shape the universe. As we explore these distant worlds and ancient galaxies, we are reminded of the fragile, precious nature of life on Earth. Each new discovery expands our awareness of the incredible diversity of planetary systems and the complex conditions under which life could emerge. K218b, with its hydrogen-rich atmosphere, potential global ocean, and hints of biologically significant molecules, represents not just a point on a map, but a symbol of humanity's enduring quest to understand the unknown. The discoveries of JWST are transforming the way we view our universe, showing that habitable environments may be far more common than once believed, and that the building blocks of life emerged early and abundantly. They also remind us that the universe is vast, dynamic, and full of surprises. Humanity has only just begun to scratch the surface of the cosmic story unfolding around us, and telescopes like JWST are our guides, illuminating the path forward. So, what do you think about K218b and the possibilities it represents? Could these carbon-based molecules and vast oceans hint at life beyond our solar system? Or are we witnessing a planet that is Earth-like in appearance but lifeless beneath its clouds? Let us know your thoughts in the comments below. And if you enjoyed this journey through the cosmos, make sure to like, subscribe, and turn on notifications to stay updated on the latest discoveries from the edge of space and time. Humanity's exploration of the universe is only beginning, and with every passing day, we move closer to answering the age-old question: are we alone in the cosmos? The universe is vast, complex, and filled with wonder, and with the James Webb Space Telescope, we are finally learning to read its story.